I'm just using the result there. All right, now let me say a couple things about these. Tell me something about these solutions. They're from what technique? They're from separation of variables, right? What do we know about solutions from separation of variables?
They're a complete basis set.
They're a complete basis set, so they're complete. All right? I also was able to normalize them at some point. So what does that mean?
The Hilbert space.
Okay, so that means they're square normalizable, which means they satisfy the Born postulate of quantum of Schrodinger's equation. Put all those together, they're Hilbert. All right, and so you guys tell me, how do I solve the most general, psi general of x and t? So this is the story that we've been doing over and over and over again.
It's the summation over n.
Summation over n of Cn
Times capital psi n of x and t.
capital, we'll just leave it like that, psi n of x and t. All right?
Times psi of n.
I did the capital psi.
Alright.
Okay? How do I find the Cn's? So now that means, because I have this nice complete basis set, what does it mean, for example? So it also means, what it means in particular over here, what's the integral of psi m star psi n dx?
1.
Psi m psi n.
Oh, no, it's
Would be 0 if m and n are not equal.
So it equals what?
no, it's delta.
It equals the Kronecker delta function of n and m. All right, which means that they're orthonormal and they have a dot product.
So you have to multiply.
So in other words, you can do what Griffiths calls Fourier's trick.
Yeah.
And so the Cn's equal the integral, and you can do because the Cn's stay constant, it equals the integral of psi, capital psi,
Psi general of
psi
x,
general
x and 0.
of x and t equals 0
Times
with
psi n
psi n of x and t
equals
equals 0
dx.
right, dx. Right, and so this comes to equal psi general of x and t equals 0, and then this becomes at t equals 0, the time dependent part comes out, so it's just psi n of x dx. Right? Same story? What did the Cn squared mean?
That's the probability density.
Okay, it's the probability that if you did the measurement on this thing, it's the probability that you would get En. So it equals the probability that if you measured energy of psi general, you'd get En. Everybody okay? Okay, a couple things, then we'll wrap this up. All right. Let's look. So let's take a look back at the stationary states. So we're looking at just the stationary states, right? Oh, I know what I wanted to do. Oh, okay, so before I do that, all right, what I want to do is the following, let's see. Okay, let me give you some homeworks and everything, but okay, so what I want to stress this is that, I guess what I want to stress is a couple things. So let me erase this for a second. Let me stress a couple things. What if you tried to solve H0 harmonic oscillator times psi n equals En psi n without the raising and lowering operators? Okay, well you would have minus h bar squared over 2m d squared psi dx squared plus 1/2 kx squared psi equals 0. Right, and you'd have to solve this, and you'd have to solve it essentially analytically. Solve analytically. All right, and what do I mean by solving it analytically? That means just go and use the turn to crank of solving partial differential equations. And it's not trivial how to solve this differential equation because of the x squared. It makes it a nonlinear differential equation, right? So when you see a nonlinear term in a differential equation, you should jump for the hills because it becomes hard. All right? It's not impossible, but it's hard. All right? And are there techniques to solve this? And the answer is yes. I am not going to do them. All right? I stressed the raising and lowering operator trick. The way to do this, and this is what I want you to do for homework, is go through this section in Griffiths, and it's section 2.3.2. So it's go through 2.3.2 in Griffiths, and you will see the full machinery of how to do it, and it's still not so trivial. Right? They do substitution, and there's lots of other tricks there. Do it. Go through that section for the appreciation. I'm not going to ask you to do it, though. All right? I mean, I'm not going to ask you on a test to be able to do it. All right? In the end, you get the following. In the end, you get that psi n of x equals m omega over pi h bar to the quarter times 1 over the square root of 2n n factorial h n of epsilon, that's my little epsilon, e to the minus epsilon squared, okay, where epsilon squared equals the stuff I had over there. Did I erase the solutions? All right, so I have to figure out what epsilon is.
Epsilon squared is
It's going to be
m omega over h bar x squared.
Is there a 2 there too? Half m omega x squared.
No, 2.
Okay.
Page 51 has epsilon is equal to 2.
Okay, so epsilon squared is m omega squared over h bar squared over h bar times x squared. All right? Okay, but the important thing is is these h's are called Hermite polynomials. So where do Hermite polynomials come from? They're polynomials that are solutions to the differential equation that looks like
The analytical.
X squared.
that looks like that.
Nonlinear.
That's right, but I mean, there's lots of other differential equations that look not like this, not just the Schrodinger's one, right? Okay, and the first few Hermite polynomials are, for example, h0 equals 1, h1 equals 2 epsilon, h2 equals 4 epsilon squared minus 2, and so on. So what I want you to do for homework, show, what do you think I want you to show for these three?
How they got those.
Not how they got those, but what do these three better be equal to?
E1, E0, E1 equal.
They better be equal to psi 0, psi 1, and psi 2. Alright, so that's another homework.
That's
Okay.
And that's 4 epsilon to the negative 2 minus 2.
4 epsilon squared.
4 epsilon squared minus 2. It's table 2.1 of page 52. Those are lowercase ties.
Yeah, I was gonna say size.
Oh, sorry. Yeah, I usually go to Digo for these. Lowercase.
Obligated decision?
Yeah, all right.
It's like third Greek
It should
alphabet.
be like, what's going on here?
Yeah, no, it's important. Thank you. All right, so that's the first thing. The second thing is let's plot a couple of these.
What was the H2 that just got wiped out there?
H2 is 4
Oh,
epsilon
oh,
squared.
right, cool.
56.
56, yeah.
Okay, and so if you look at figure 2.7 on page 58 is they plot some of those. So if you plot, and what we'll do over here is, it looks just like a harmonic oscillator. Here's x equals 0. Here's the potential, guys. It looks just like a harmonic oscillator. And if you plot, for example, psi 0, it looks like this. It looks like this. That's psi 0. And then psi 1 looks like this. Okay, a little less pronounced there. But clearly, and these are the stationary states, all right? These are the stationary states. But what we really want, and maybe I'll do this just in a different color, is to plot. Sorry, the blue is psi, but what we want is psi n squared, right? Because what is that?
What's our square? Our normalizable
Probability that.
probability.
That is our probability density for the stationary states, right? This is the probability density for the stationary states. And when you plot these, of course, this first one looks like this. All right, and when you plot this one, it looks like this. All right, and when you get to n equals huge, when you get to n equals huge, it looks like this. I'm not giving this justice at all. So please look in your book.
Looks like B1 over sin x.
Well, let me give you it looks like this. All right, so high n. And last year, Dale plotted these, and I think I put it on a blackboard of the plots that Dale did in Excel, and it wasn't trivial to do, so I won't ask you to do it. All right, but Dale did this, and so by all means, look at what he did in Maple on Blackboard. All right, but the cool thing about it is for a large n, when n gets very big, right? Where is the probability highest to find a harmonic oscillator?
Right in the center.
No,
Yeah.
edges.
ends.
Right in the ends. And so what do we know about a ball? When you put a ball